So you have a telescope and now you've got to figure out where to put it. You want to definitely choose someplace with decent weather. So Minnesota's not recommended. We have a lot of clouds all winter long. So you want clear skies, not a whole lot of rain. Hurricanes, also a bad idea. You probably want to get as high up as you can, because maybe you can be above the clouds, maybe you can be above the weather. Also, the amount of air and water vapor that are above you absorb a lot of the colors of light, or invisible colors of light. So we'll talk about that a little bit more in a second. You want it to be accessible. You want to have roads and electricity to be able to get to your location and the people to be able to get back and forth. Indoor plumbing is also a benefit. And light pollution. So you don't want to build it in a city like this lovely figure shows us. Hopefully, if you look at this, you'll realize it's photoshopped. Half the sun is in daytime, and in this picture, all of Earth is at night. There's also no clouds, so this has been mosaicked together. But the point still stands. So you want to be as high up as you can to get above the air, because if you're on the ground, so I'm going to click on the ground here and observe a star from the ground. When you look at the stars from the ground, they appear to twinkle. And that's caused by the atmosphere. And if you were to take a picture of that twinkling and leave your camera shutter open for a while, in this case 15 seconds, it's going to look blurry because your target is moving. If you can build it up higher, build your observatory up higher, you'll be above some of the air. So the amount of twinkling is less, and your picture is clearer. So let me flip back to the ground. Blurrier, a little bit clearer. If you had enough money, you can go up to space. If you're in space, there's no atmosphere, there is no twinkling. Stars do not twinkle if you're up in space. And then you could leave your shutter open as long as you wanted, and you're going to get a nice clean image. So what causes the twinkling? It's basically turbulence in the Earth's atmosphere, but it's also the different temperatures as you go through the different layers of the atmosphere. But here we have a little image. Starlight is going to be trying to come down through the air, and as it approaches an air mass, it will refract a little bit, bend a little bit, and every time it reaches a new density, a new temperature, it'll refract just a little bit differently, and your image of a star will end up somewhere. And give it a second, give it a minute, the air masses will shift, and that makes your image of your star dance around a little bit. If you were on the ground looking up, what you would see is the image of the star being brightest when the image perfectly aligns to you, and then when it shifts off you a little bit, it'll be dimmer. So it'll be brighter, dimmer, brighter, dimmer. It can also twinkle a little bit in color, because when the light refracts through the air, it can twinkle in color. The colors can get separated. So it can be a little bit bluish and reddish as you watch it twinkle. I like to think of the atmosphere as an ocean. We live under an ocean of air. So if you wanted to think about this, but with an everyday example, think of yourself looking into a pool of choppy water. When the water is nice and calm, there's no turbulence, there's no kids in there rippling the water, you can see the bottom of a swimming pool really clearly. The black lines look very straight. But put 50 kids in there, get the water nice and choppy, and all of a sudden it's hard to see the bottom of the pool clearly. The edges of the black lines will be jumping all over the place. They don't look so clean and organized. Since we have supercomputers now we can do a trick called adaptive optics to try to undo the twinkle. we undo the twinkle now so we can do really good astronomy from the ground. By looking through all the air, we can actually pretend it doesn't exist. So, adaptive optics. What adaptive optics does is you have your telescope and you have a high-powered laser and you shoot it into the sky. And when you do that, what you would see if you were looking down the beam is you would see a false star. So let's draw in the false star here. So you shot the laser beam up there. You know exactly where it should be pointing. But that laser beam has to travel through the air to get up to the higher atmosphere. It creates the dot, and then it comes back to you. So that laser beam, that light that you see, went through the air twice. So what your computer does is it says, that laser beam, that false star, isn't exactly where I shot it. It's been moved a little bit. The atmosphere has refracted it a little bit. It doesn't appear here. Maybe it appears over here now. So let's change the optics. Let's change the shape of my telescope to force that false star back on the image where it was supposed to be. And so it does those calculations several times a second. Where is the false star? Where should it have been? Change the telescope shape to put it back where it should be. Several times a second. Right? And it does that usually by having a mirror that's deformable, meaning it can push and pull it. So we have secondary mirrors now, the little mirrors, with hundreds of motors glued on the back of them. And several times a second, it pushes and pulls and it shapes the mirror so it's a little bit wobbly to always put that false star, that green laser point, back where it was supposed to be. And when you do that, you're also doing it for the light of the galaxy that's coming in. And you're going to get a much clearer image of it. So you're basically correcting for twinkling several times a second using supercomputers, a deformable mirror, and you can undo the effects of the atmosphere, which is amazing that technology can do that now. So we now have telescopes on the ground that can do visible astronomy better than Hubble. We can do better than Hubble now on the ground. So we still use Hubble. Why would we still use Hubble if we can do better astronomy in the visible light on the ground? Hubble doesn't only do visible light, right? Let me click forward and slide. Right? The Hubble, which happens to be about the size of a school bus, observes visible light, ultraviolet light, and some infrared light. Okay. So now, if we were going to do visible astronomy, we wouldn't pay to put it in space. We would just build it on the ground to give it a gigantic laser and some supercomputers and call it good. But Hubble still does ultraviolet and infrared, which can't reach the ground. Right? So here's all the bands of light: gamma ray, X-ray, ultraviolet, visible, infrared, radio. And only 2 of those bands actually have the light reach the ground. So you can do visible astronomy from the ground, and now we can do it really well. And you can do radio astronomy from the ground. Great. But if you want to do any of these others, gamma rays come from space, but they get absorbed by the atmosphere. That's actually good for us. It protects our biology. Our atmosphere shields us. X-rays are absorbed in the atmosphere. Ultraviolet, most of it, right? Even though we'll still get sunburns, most of it is blocked by the atmosphere. And infrared is blocked by the atmosphere. So if you want to observe any of those, you want to do infrared astronomy, X-ray astronomy, you need to go up higher. Maybe a plane, maybe a high altitude balloon, maybe a satellite. This airplane, by the way, is representing a specific airplane, and if you think engineering is cool, you should definitely Google that airplane. It's Sophia, S-O-F-I-A. It's an engineering feat. It's amazing. So we still use Hubble. We're not going to repair it anymore once it quits. It's dead. It's going to be space junk. But while it's still working, we're still using it to observe what we can. It's still doing a good job, doing ultraviolet and an infrared light. Before we launched Hubble, this was the best we could do from the ground. And this happens to be a picture of a star called Eta Carina. It's dying, it's throwing off a lot of mass. And that's the best we had ever seen it. We launched Hubble. Hubble ended up to be, I think it was nearsighted. It needed glasses. Launched another mission to fix it, give it glasses. And then we were able to see Eta Carina like this, like we had never seen it before. It was cutting edge astronomy once Hubble was fixed. It was great. So maybe you guys are interested. The Hubble mirror was ground into a very specific shape, and they could have done a test with lasers to check the shape of the mirror, make sure it was ground correctly. The test would have cost, I think, a couple $1,000,000. They decided to try to save the money, and this is NASA, and this is government money, so they're going to try to save a couple $1,000,000. Presume it was ground correctly and the mirror's the right shape. Launch it into orbit, open up the telescope. The data we get back is obviously out of focus. Hubble's mirror was not ground correctly, so now you have to launch a whole new space mission to correct it. Probably cost billions of dollars. Careful where you cut your corners. The most famous infrared telescope is called Spitzer. Spitzer is now operating in what we would call warm mode. Right? Remember, infrared is given off by objects that are warm. So your body glows in the infrared, the table glows in the infrared. And stuff out in space, even if it's fairly cold, can give off a little bit of infrared. And so this telescope had to stay really cold in order to be able to observe really faint infrared light from space. Now, if it was too warm, it would glow infrared and blind itself. So it had a solar panel shield, well, still has a shield to keep the sunlight off of it, but it also had liquid helium and liquid nitrogen as coolants to keep it extra cold, and it's run out of them. So now Spitzer is a little bit too warm. It's not as efficient anymore. It's not as great, but it's still up in space, observing in the infrared. You would want to launch a telescope like this if you wanted to, say, study star forming regions. So you could look at a galaxy and you could see all the star forming regions. They emit infrared light. This is what it would look like in the visible. You get to study different things by looking at different light. Forming planets, forming solar systems, very distant galaxies, those are all done mostly in the infrared. Chandra is the most famous and advanced X-ray telescope that we have right now. It has to be built a little bit differently because you're catching a different type of light. And if you were to shine an X-ray just straight at a mirror, the X-ray would just see it like a concrete wall. It wouldn't reflect, it would just absorb into the concrete wall. So you can't just shoot X-rays straight at a mirror and have them reflect to your camera. So what this does is it uses, we call these nested mirrors. They're like cylinders, but the mirrors are tapered on one end, and they're tapered on one end so that way the X-ray doesn't, bam, doesn't hit right into the mirror, we tilt the mirror so it just skims it and glances off. And in that case, the X-ray will not get absorbed. It will reflect towards your camera. So you have to do it gently. You have to tip the X-rays a little bit at a time. So with Chandra, you can see some cool stuff that we'd gotten some great images of stuff we hadn't seen before. Neutron stars, accretion disks around black holes glow in the X-ray. I have a picture in a second, in a few slides, from Chandra. Radio. Different energy of light, so you build your telescope a little bit differently. Two ways that radio telescopes are different is radio waves are not picky. They don't need a nice shiny mirror. They only need a metal dish. Right? And the metal dish will act like a nice shiny mirror to radio waves. So that's what these are down here in the picture, is just metal dishes. Okay. So VLA, the very large array, we really named it that, is just an array of large metal dishes. And I do mean large. There's a building right there for people. There's a radio telescope. Okay. The second thing about radio waves that's different and affects how you build your telescope is radio waves have a really long wavelength. Right? Visible light has a tiny wavelength, nanometers, smaller than I can show you. Radio waves can have a wavelength of a meter, 3 feet, 5 feet, 10 feet. They have huge wavelengths. So if you want any kind of resolution, if you actually want to see what's going on, see the detail, what that means is you have to build a huge telescope in order to get any kind of detail. In order to get any resolution, you need a huge telescope. So we use a trick called interferometry to get that detail without building one ginormous telescope. What you do is you build a series of them, 1, 2, 3, so on. Build a lot of the telescopes. And then you take their signals and you put them into a computer, and the computer it's going to act like one giant telescope that's this big. So if you put all the signals together in the right way and interfere them in just the right way, what you're going to do is you're going to get an image quality that mimics a telescope of that size. So it's great. You don't have to build a telescope that's 3 miles across. You can build little telescopes dotted along 3 miles. Right. So you can get a gorgeous picture from the internet and download it and make it your desktop, and it might be representing what you would see with the human eye, like the one we showed you before, the one with the red picture that was taken with the red filter, a green picture that was taken with a green filter, a blue picture that was taken with a blue filter, and you put it together, that mimics what the human eye would see. This picture does not mimic what the human eye would see. So in Photoshop, or the free version that we use, GIMP, you would have data from X-rays. X-rays are invisible, so you'd have to give them a color if you want people to see it. So we'll give it blue. On the low end of the spectra, infrared, we have to give it a color so we can see it. So let's pick something low end, low energy, maybe red or orange. So there's your Spitzer data, color-coded orange. Your visible light, let's pick green. Could have picked yellow, let's pick green. When you add them all together, you get a lovely image, but it's not mimicking what the human eye would see at all. It's all true, but it's not what it would look like to you. So whenever you see an astronomy picture, look for the caption to actually know what you're looking at. Here's an example of looking at one object in different bands of light to see what we can learn, to see how it looks different. So this is an exploded star. It went supernova and blew up. This is what it looks like in the visible light. Let's switch to infrared. You can see the cooler gas and dust glowing around it, giving off infrared. Switch to radio. Radio would come from the coolest gas. Radio light also comes from electrons that are trapped in magnetic fields too, so if there's any strong magnetic fields, we'd be able to see that here. And the X-ray, you can see the highest energy stuff giving off X-rays, and in this case there's a neutron star down in here, a collapsed core of a star, really intense gravity, and it will energize and affect the gas around it. So the neutron star is down in the middle. Right. So a second example, how about a nebula in the disk of the Milky Way? Let's look at this nebula. So you see the dark parts? That's the gas and the dust. It's dense enough to block out the starlight behind it. And this happens to be dense enough where it might be forming stars. So let's switch to look at the infrared. The gas and dust is just warm enough to glow in the infrared. Let's go to the mid-infrared, deeper into the infrared, and that nebula really does glow a lot more. So you switch the band of light you're looking at, you can switch what you're studying. That looks like a forming star region. There, there, there.